So thank you for being here. I'll let you present.
Thank you so much. I think there was somebody from China, but we do come from very far. And thank you so much. Actually, we're very happy to be here because, so we work in a hospital, and I'll just take a few minutes to tell you a bit the background or where we come and what we're trying to do. But it's really nice to see, the latest state-of-the-art technology and people like you. And I think there's a way we can collaborate together. So my colleague Wasim, who is much smarter than me, will tell you more about the dynamic texture mapping for topological changing volumes that we worked on. Just very briefly, I'll tell you about our team and then the kind of collaboration we tried to put together. There might be some interest. So our team is based in, I have also to say we have another colleague, George Yunus, who's not here today, but he also worked on this project. So we are based in Hamad Medical Corporation. So Qatar is very small, so Qatar is about 4 million people, maybe, so it's not a big country, but the Hamad Medical Corporation is a national hospital and basically treats about more than 90% of the healthcare of the country. So we're very fortunate to be a part of the hospital, so we have access to the patient and to the data and to the doctors. Now, we work within the Department of Surgery, and we're not, we do publications, we do patents, etc. But our main goal is to really work on technology-based projects to basically influence and help the patient care. And that's why I think there's maybe a lot of collaboration we can set up together to create products that we can use within our hospital, test and use within our hospitals to really improve the patient care rather than being more of an academic effort. So I just want to tell you about a quick funding scheme that is based in Qatar, so the Qatar National Research Fund. I know that you probably are very well funded here in Europe. You've got a lot of research funding, but this particular research funding scheme allows for international partners. So the nice thing about this is that it explicitly encourages international partners like French. We actually had some partners in France, in the UK, in the US, and it allows for companies as well, about $1 million for 3 years, and the next call is in February. So if you're interested, we can talk more later. So back to the more the core of what we're doing. So one example of the context of this work is one particular project that we wanted to develop is to simulate the robotic one of the steps in robotic prostatectomy, which is the urethral transaction step. And so this is a missing step in most of the commercial simulators. And we found out that actually it's to do this, you need to do it in a highly realistic way. And to do this, you need to do the remeshing and then the physics, and it's quite complicated. And in fact, so what we wanted, the goal was to develop a tool that we can discriminate between the surgeons and the novice. And so, while working on that, we actually developed so we have an in-house developed simulator that you can see is not super perfect, has some glitches, but in terms of textures and some of the cutting, it actually works quite well. So we want also, so to do that, we wanted to benchmark, in fact, and that's why, so wanted to compare our cutting simulator with the cutting that is in SOFA and then the upcoming cutting. And that's why we thought to do the texture mapping, and that's why we started using SOFA. I think now you can.
Yes. Thank you. So we started, that's working, right? Okay. We started working, looking into different frameworks, and SOFA stood out as an open source framework, and it's widely used. And we wanted to see how it would compare against our internal simulator that we have. And to also look at other added value that SOFA provides, such as we were really intrigued by the scene graph and the fast prototyping that it allows, that SOFA gives us. To implement the same, to have a similar environment in SOFA, we were looking into what's available and what we might need to introduce to have a similar scenario implemented in SOFA. And in the future, when Infinitec implements the remeshed cutting, we could compare it against our own and see how it fares. So two things were missing. If we look at our simulation used Geomagic tools, and SOFA has a plugin for that. So one line in the XML, and we have the tools ready, deformations already available, and For cutting, there's a plugin called Sofa Carving, and this basically deletes text. It does not do remeshing in the sense it doesn't subdivide text, but Infinitec's working on that, and that's what we are working on as well, and we have for our internal simulator. Now the next one is the thing that is missing is UV mapping, and that's the whole topic that I want to talk about. And SOFA has UV mapping for OBJ files, that's surface meshes, made of triangles. But for volumetric meshes, they don't support UV mapping yet, and this is what we are trying to introduce. This helps add realism to the simulations and give context to the user. So this is the end result. This is in SOFA right now. All the meshes you see are volumetric, tetrahedral meshes, and this is the scenario, the urethral transection scene that we have in our internal simulator, and now we have it in SOFA. And how do we do the UV mapping? So there are some steps before we get into SOFA, which is we take a tetrahedral mesh, extract the surface mesh out of it, and then we just take any 3D editor. We use Blender to do UV mapping, texturing, however you want it. And then we have a custom utility which maps these UV coordinates from the surface mesh back to the tetrahedral mesh. So we have a UV mapped volumetric mesh. So right now we are texturing the outer surface, and it's also possible to add textures to the inner triangles of the tetrahedron. Once we have this texture mapped, we just load it into SOFA. We use SOFA Python to do all this, and it was really easy to use SOFA Python based on the documentation and looking at the source code. We can access all the variables necessary to achieve this. Once we took read the texture file in SOFA, we take the UV mapping and apply it to the volumetric meshes. But the issue with volumetric meshes is they don't have all the triangles are connected to each other in the sense the vertices. If you take two triangles, all the vertices are between the two triangles. The two vertices would be shared, and that means you cannot uniquely identify a vertex per face. And I looked into how OBJ Loader does it. They have a flag called handle seams. In that, they duplicate the triangles so they can have UV coordinates per vertex per face. And that's what we've implemented in SOFA using SOFA Python. We take the volumetric mesh and then we duplicate the triangles of the surface to visualize it. And along with that, most of our meshes that we use are OVM meshes, and this is a data structure for storing meshes made by INRIA and RWTH. It's a university institution, and what OVM provides is the library provides efficient topological updates, and we can do carving or remeshing in a more efficient way by using OVM topology. But right now we don't have the topology, but just OVM loader to load the files into SOFA. Then we just use the readily available tetrahedron topology that SOFA provides. And it also allows you to embed custom tags, properties, and we use that to incorporate the UV data into the OVMS. So it's a single file. You can load the textures, texture coordinates, and the mesh data. And once you have the textured OVMs loaded, you can see that we have done some carving. It's a screenshot, not a video. But even after you carve, we retain the texture coordinates, and the internal faces that are exposed have just a generic color, and they're not textured. But in our internal simulator, we just didn't implement it here. We have use a Berlin noise function, which generates 3D noise, and we can apply it to the inner surface to generate a dynamic noise texture. And this is just a clip of what we are working on. This is using PBR, physically based rendering. That's what Unreal uses as well to make it look very realistic. And this is just a render using Blender, but we are right now working on incorporating that into our simulator. Thank you.
Thank thank you very much for the presentation. Again, I just heard it's not bad for the rendering, which is really nice. I think for rendering, would definitely be. I think there is a lot of things to do with these features in SOFA. I have already one question here. Is there any other question in the room? On another just here.
Thank you. I think it's very nice looking work, and I know a team in Strasbourg, but I think there are several around the world who are working on synthetic texture generation using very advanced methods that basically can create a texture on the fly, as far as I understand, from examples from real textures. So basically, I think that there are people who are knowledgeable about the way you could create even more realistic textures when you carve than just picking some color and maybe go beyond what you are doing now. Maybe we can put you in touch with them. I don't know if their code is available like that or not, but I think it's already very nice looking, for sure. But knowing surgeons and how picky they can be about the visual realism, I think there are people who know how to make it look even better.
Definitely, that would be great.
We're actually struggling with that. That will help us actually. It can connect us with these people. Absolutely, yeah. We'll do that.
Our current implementation does not have plain internal faces. We use 3D noise and use the 3D position of it to generate a slice of noise texture that can be customized to how we want it to appear. But it's not based on existing images. That would be much better. Thank you.
Yeah, I have a question about this precisely. Where do you get the data? Where do you get the data necessary to create this internal texture? And how do you map it to the triangles?
Internally,
Yes.
not the external ones. For the internal ones, what we use is that, so when you have 3D texture, basically 3D noise, you can have the coordinates of, the UV coordinates for 3D noise would be X, Y, Z. So we just take non-deformed position of the internal triangles. So even in the case where we remesh and we introduce new triangles, we can take the 3D position when it's not deformed and stick it to that position. That would be the UV coordinate. In the 2D case, you would have.
Okay, I understand the mapping, but you're generating noise. That's not real data. That's noise.
Yeah. But if we have a 3D texture, that's a 3D cubic texture that we have pre-generated, we could still use the 3D XYZ coordinate to get.
Okay.
It works the same for both.
Okay, thank you, Wasim.